Imagine asking a humanoid robot to open a door, walk over, reach for the handle, turn it, push, walk through. For a person, that's barely a task. We don't think about where our feet should go, how hard to turn the handle, or how much force the door will need. We just adjust. A robot has to figure out what to adjust and when. It has to see the door, locate the handle, position its body, reach without falling, make contact, apply the right force, and react as the door moves. And the door itself isn't perfectly predictable. The handle might be slightly different, the hinge might be stiff, the floor might be uneven. A person barely notices these differences. The body simply compensates. That becomes much harder when the robot starts walking. Every step changes the position of its weight. The foot may land slightly differently than expected. The ground may not be perfectly level. The body has to keep making small corrections before a small disturbance becomes a fall. Humans do this constantly without thinking about it. A humanoid robot has to sense what is happening and produce those corrections through motors, sensors, and control software. And walking is only the beginning. Once the robot starts using its hands, another layer of difficulty appears. Consider a cup. Recognizing the cup is relatively easy. Knowing how to hold it is not. A person reaches out, makes contact, and adjusts the grip almost automatically. If the cup is heavier than expected, the hand compensates. If it starts to slip, the fingers change their force. If the surface is wet, the grip changes again. The important information isn't only coming from the robot's cameras. It is happening at the point where the hand touches the object. That is why tactile sensing matters. A robot needs to know not just what it is looking at, but what is actually happening when its body comes into contact with something. And that problem gets harder when the object itself can change. A cup has a fairly predictable shape. A shirt doesn't. Neither does a towel, a plastic bag, a cable, or a pile of clothes. These objects can bend, fold, stretch, collapse, and move as soon as they are touched. There may not even be one obvious place to grab them. For a person, picking up a shirt is almost automatic. For a robot, the thing it is trying to control can change shape while it is being handled. This is where the robot's body becomes one system rather than a collection of separate parts. Reach forward with one arm and its balance changes. Pick up something heavy and the center of mass moves. Push against a surface and that force travels back through the body. The hand may be doing the obvious work, but the legs and torso are involved too. A humanoid can't always solve these problems by controlling one limb at a time. Its whole body has to coordinate around the interaction. And there is a physical limit underneath all of this. Energy. A human can walk around, lift something, sit down, stand up, and keep going without carrying a power source. A humanoid robot has to carry its own. Every motor needs energy. Walking uses it. Holding a position uses it. Moving quickly uses more. Carrying a heavy object uses more again. So making the robot stronger doesn't simply solve the problem. More powerful motors can add weight. More weight makes the robot harder to move. That increases the energy required. More energy can mean a larger battery, which adds even more weight. Change one part of the robot, and other parts have to compensate. But even a robot that solves all of these problems still faces a much simpler question. Can it keep doing the job? A demonstration can show a robot picking up an object successfully. A useful machine has to do it again and again, not 10 times. Not under carefully controlled conditions, thousands of times while the environment changes around it. A real workplace has people moving through the same space. Objects end up in slightly different places. Something eventually goes wrong. When it does, the robot has to recover or someone has to step in. And if that happens too often, the robot may spend too much time waiting for help, being repaired, or sitting idle. That changes the problem completely. A robot doesn't just have to be capable, it has to be reliable enough to be worth using. Now comes the question that makes the whole idea of a humanoid robot more interesting. Why make it humanoid at all? A wheeled robot is easier to balance. A specialized robotic arm can be faster and more precise. A machine designed for one task doesn't need to walk, balance, grasp, and navigate at the same time. So why give a machine 2 legs, 2 arms, and human-like hands? Because the environment already has them. Doors have handles, buildings have stairs, shelves are built around human reach. Tools are shaped for human hands. Factories, warehouses, kitchens, hospitals, and homes were all designed around the human body. A humanoid robot is difficult partly because it is being asked to operate in a world that was never designed for robots. But that is also why the shape is useful. Instead of rebuilding the world around machines, engineers are trying to make machines capable of using the world we already built. And that creates the paradox. The human body looks simple from the outside, 2 legs, 2 arms, 2 hands, but that simple shape hides a surprising amount of complexity. It knows when the ground feels different. It knows when something is slipping. It knows how hard to push. It knows how to shift its weight. And when something unexpected happens, it can change what it is doing almost immediately. Most of this happens without conscious thought. We don't notice it, because these abilities have become ordinary to us. For a humanoid robot, none of them are ordinary. Balance has to be engineered, touch has to be sensed, movement has to be coordinated, energy has to be managed, failures have to be recovered from, and all of it has to work together in a physical world that rarely behaves exactly the same way twice. That is why the hardest part of building a humanoid robot isn't making it look human. It isn't even making it walk. The difficult part comes after it starts moving. It has to interact with objects that don't always behave the same way. It has to respond to a world that doesn't stay still. It has to coordinate its entire body while using limited energy. Humans make this look ordinary. That is what makes it so difficult to reproduce. Because the real challenge isn't teaching a robot to move like a human. It's teaching a machine to live in a world built for humans.